Welcome back to Scientific Discovery Hub, the channel where we unravel the universe's greatest mysteries. Have you ever wondered if a single object could hold secrets older than our entire solar system? Today, we're diving into one of the most fascinating cosmic puzzles of our time, the enigmatic interstellar comet 3I Atlas, discovered in 2025. This icy traveler from the depths of the Milky Way has sparked a fiery debate among scientists. Is it 3 billion years old, or a staggering 7 billion years? The answer could rewrite our understanding of the universe's history. So what's the big deal about 3I Atlas? For starters, it's only the third interstellar object ever spotted visiting our solar system. Unlike asteroids or comets born here, 3I Atlas arrived from the Milky Way's thick disk, a region teeming with ancient stars. But here's the twist. Some studies suggest it's ancient, older than Earth itself, while others argue it's relatively young. How can the same object have two vastly different ages? In this video, we'll break down the science behind the debate, exploring everything from cosmic highways that guide interstellar travelers to the chemistry of its icy heart. We'll start by decoding how scientists estimate 3I Atlas's age, using clues from its origin and motion through the galaxy. Then we'll map its hyperbolic escape route, revealing why it's truly an outsider from beyond our solar system. You'll discover how its chemical makeup, filled with carbon dioxide, water ice, and even cyanide, hints at a unique formation story. Along the way, we'll explore the Milky Way's layered structure, the role of stellar archaeology dating cosmic objects, and the challenges of spotting interstellar visitors hiding in plain sight. But this isn't just about numbers. The age of 3I Atlas forces us to confront big questions. How do galaxies evolve? Can comets survive for billions of years in space? And could interstellar visitors like 3I Atlas carry the building blocks of life? Whether you're a space enthusiast or new to astronomy, this video will take you on a journey through time, from the Milky Way's violent past to the future of cosmic exploration. Ready to crack the code of 3I Atlas? Hit play, subscribe for more mind-bending science, and join us as we explore the universe, one mystery at a time. Let's begin. What if a single object could hold secrets older than our solar system? What if a frozen wanderer, hurtling through the void at breakneck speed, carried within it the echoes of a time when galaxies were young and stars burned inches unfamiliar constellations? 3I Atlas, the third confirmed interstellar comet to traverse our cosmic neighborhood, has ignited a profound question. Is it truly a relic from the early Milky Way, older than the cradle of life itself? This is not merely a matter of numbers, a contest between 7 billion and 3 billion years, but a collision of timelines, a dance between the fleeting present and the unfathomable deep past. To grasp the significance of 3I Atlas's age is to confront the scale of existence itself. In the grand theater of the cosmos, where eons blur into geological instants, this comet becomes a timekeeper, a silent witness to epochs we can barely imagine. Its journey is a bridge between the birth of galaxies and the fragile, transient world we call home. The answer lies in the comet's trajectory and its velocity, a language written in the mathematics of motion. 3I Atlas entered the solar system on a hyperbolic path, a trajectory so steeply curved by the sun's gravity that it will escape back into interstellar space, never to return. This path is key, unlike asteroids or comets native to our system, which are bound to the sun in elliptical orbits. Interstellar objects arrive from beyond the gravitational embrace of any star. Their trajectories are dictated by the galactic tides, the slow churn of the Milky Way's spiral arms, and the unseen currents of dark matter. By tracing 3I Atlas's path backward, astronomers determined it originated from the direction of the constellation Sagittarius, near the galactic center. More precisely, its velocity components, radial, transverse volts, and vertical watts, revealed a startling truth. The comet hails from the Milky Way's thick disk. This is a region distinct from the thin disk, where our solar system resides. The thick disk is a cosmic attic, a repository of ancient stars formed billions of years ago. Long before the thin disk coalesced into its orderly spiral, stars inches the thick disk are older, metal poor, and often orbiting the galaxy on inclined paths that take them far above or below the galactic plane. If 3I Atlas shares this heritage, then it too must be ancient, but how old? The answer hinges on stellar populations. The thick disk is estimated to contain stars ranging from 7 to 14 billion years old, many predating the formation of the solar system 4.6 billion years ago. AMPA's 2025 study, led by Matthew Hopkins and collaborators, analyzed the comet's velocity and position relative to nearby stars, concluding with 68% confidence that 3I Atlas is between 7.6 and 14 billion years old. However, another team, led by Asta Taylor and Darrell Seligman, proposed a narrower range, 3 to 11 billion years. The discrepancy arises from differing assumptions about the galactic environment. Hopkins' team emphasized the thick disk's association with ancient stars, while Taylor and Seligman considered dynamical interactions, how the comet might have been flung from its home system by gravitational slingshots or stellar encounters. Both conclusions are valid within their frameworks, but they highlight the ambiguity inherent in decoding the age of something that has traveled across the galaxy unobserved until now. This uncertainty is the heart of the mystery. Is 3I Atlas a relic from the dawn of the Milky Way, a time when the first stars flickered into existence and the galaxy was still assembling its spiral structure? Or is it a middle-aged traveler, born inches a distant system that has since evolved into something unrecognizable? The answer depends not only on the comet's velocity, but on the physics of its composition. If 3I Atlas is indeed 7 billion years old, it predates the solar system by 2.4 billion years. This would make it one of the oldest known objects in the universe, a time capsule from an era when the Milky Way was young and chaotic. Such an age raises profound questions about the stability of planetary systems. How could a comet survive intact for so long, navigating the gravitational tides of the galaxy without being shattered or absorbed by a star? Most comets in our own system originate from the Oort cloud, a distant reservoir of icy bodies that formed alongside the planets. Yet 3I Atlas's origin is far removed from such familiar structures. Its age suggests it may have formed a star system that no longer exists, or a region of the galaxy where conditions were vastly different. Consider the implications for astrobiology. If 3I Atlas carries organic molecules, carbon monoxide, cyanide, and carbonyl sulfide, as observed by the James Webb and Very Large Telescopes, its chemistry could reflect the primordial soup of an ancient protoplanetary disk. These compounds are essential building blocks for life, but their presence in an interstellar comet raises questions about the universality of life's ingredients. Did similar processes occur in every star-forming region of the galaxy? Or is our solar system unique? The comet's age adds another layer. If its chemistry dates back 7 billion years, it might preserve materials untouched by subsequent stellar generations, offering a glimpse into the chemical evolution of the Milky Way itself. Moreover, 3I Atlas's journey challenges our understanding of the Milky Way's structure. The thick disk is a dynamic place, where stars migrate vertically and horizontally over cosmic timescales. If the comet's origin is tied to this region, it implies that interstellar objects are not just rare visitors, but part of a larger galactic ecosystem. Perhaps comets like 3I Atlas are ejected regularly from the thick disk, their trajectories shaped by the gravitational pull of massive stars or the passage of molecular clouds. Such a scenario would mean that the galaxy is a vast interconnected web of exchanges, where material from one system can seed another. In this light, 3I Atlas is not an anomaly, but a messenger, an emissary of the Milky Way's hidden history, yet the debate over its age persists. AMPA's 3 billion-year-old 3I Atlas would still be ancient by terrestrial standards, but far younger than the thick disk. This would place it in the thin disk's later evolutionary phase, a time when star formation was still active, but the galaxy's structure was beginning to stabilize. Here, the comet might have formed a system disrupted by supernovae or binary star interactions, ejected into interstellar space by the same forces that sculpted the solar system's outer reaches. Either way, its presence underscores the impermanence of planetary systems. Just as the Oort cloud is a graveyard of our solar system's discarded debris, The galaxy itself may be a cosmic necropolis, littered with the remnants of civilizations and worlds that will never meet. To unravel the enigma of 3I Atlas's age, we must first ask, how do we even define interstellar inches, a universe teeming with motion? The term implies a boundary, a distinction between what is native and what is alien, yet the cosmos offers no such clear lines. Galaxies collide, stars trade material, and the very fabric of space is woven with the threads of gravitational influence. Interstellar objects are not just visitors, they are testaments to the fluidity of the universe, to the ceaseless exchange of energy and matter across unimaginable distances. In the next segment, we will trace the cosmic highways that brought 3I Atlas to our doorstep. We will explore the gravitational slingshots and stellar encounters that shape the trajectories of interstellar travelers, and examine how these objects challenge our definitions of belonging in the universe. For 3I Atlas is not just a relic of the past, it is a harbinger of the future, a reminder that the Milky Way is not a static stage but a living, breathing entity. As we follow its path, we step into the vast, uncharted territory where the boundaries between self and other dissolve, and the universe reveals itself as an endless conversation of light and shadow. In the vast, silent expanse of the cosmos, where galaxies spiral like painted brushstrokes and stars flicker like ancient sentinels, a lone traveler emerged from the unknown. On 1 July 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS, telescope at Rio Hurtado, Chile, captured a faint smudge of light against the backdrop of the Milky Way. What began as a mere speck inches the night sky soon revealed itself to be something extraordinary. 3I Atlas, the third confirmed interstellar object to ever grace the solar system. This comet, hurtling through space at a blistering 58 kilometers per second, was not born among the familiar planets and asteroids of our cosmic neighborhood. Its origin lies far beyond the boundaries of the sun's gravitational embrace, carried on the tides of interstellar currents. As it approached its hyperbolic path, a trajectory bent only briefly by the sun's pull, before fleeing back into the void, spoke volumes about its alien heritage. Unlike the comets that have danced through the inner solar system for millennia, 3I Atlas was not a native of the Oort cloud or the Kuiper belt. It was a relic from another star system, a wanderer from the distant reaches of the Milky Way. The discovery of 3I Atlas marked a pivotal moment in humanity's quest to understand the universe. It was the third such interstellar visitor, following the enigmatic 1I Oumuamua in 2017. Yet 3I Atlas carried with it secrets even deeper than its predecessors. Its journey, traced backward through the fabric of space-time, pointed to the Milky Way's thick disk, a region teeming with ancient stars, where the light of the galactic center glows like a primordial beacon. To astronomers, this meant 3I Atlas was not merely a traveler. It was a messenger from an era when the galaxy itself was young, its stars still settling into the grand architecture of the cosmos. As telescopes across Earth and Inch's orbit turned their gaze toward this interstellar voyager, they began to unravel its story. What could this object teach us about the birth of planetary systems? How had it survived the eons of interstellar travel? And what did its arrival mean for our understanding of the universe's interconnectedness? In the quiet hum of the cosmos, 3I Atlas was not just a fleeting visitor. It was a bridge between worlds, a whisper from the past carried by the winds of space. The journey of 3I Atlas began long before its discovery in 2025. By the time it entered the inner solar system, it was already a veteran of the void. Having traversed the immense distances between stars, its hyperbolic trajectory, a path that curves around the sun and then escapes into deep space, was unmistakable evidence of its interstellar origin. Unlike comets bound to the solar system by gravity, which follow elliptical orbits, 3I Atlas's path was unbound, its velocity exceeding the escape velocity of the sun. This meant it had not originated here. It had come from somewhere else entirely. To determine the comet's true origin, astronomers dissected its motion into three components: radial, transverse, and vertical velocitive to the galactic plane. When 3I Atlas entered the solar system, It was moving away from the galactic center at a radial velocity of -51.0 kilometers per second. These numbers placed it firmly within the thick disk of the Milky Way, a region characterized by older stars and a higher concentration of heavy elements. The thick disk, unlike the younger thin disk where the Sun resides, is a remnant of the galaxy's turbulent past, formed by mergers with smaller dwarf galaxies and the gravitational churn of ancient stellar populations. For 3I Atlas to hail from this region was a revelation. It implied that the comet was not a recent interstellar nomad, but a survivor from the early days of the galaxy itself. The comet's arrival at the solar system was not a random event. Its trajectory intersected the plane of the Milky Way near the galactic center, a region dense with stars and dark matter. This location suggested that 3I Atlas had been ejected from a distant planetary system, perhaps during the chaotic youth of its host star. Such ejections are common in young stellar systems, where gravitational interactions between planets can hurl comets and asteroids into the void. Once free of their home system's gravity, these objects become interstellar drifters, wandering the galaxy until they encounter another star. For 3I Atlas, that encounter was with the Sun, a fleeting rendezvous that would last mere decades before it resumed its journey through the cosmos. The discovery of 3I Atlas was not immediate. When the Atlas telescope first detected the object, it was faint, with an apparent magnitude of 18 barely visible even to large telescopes. Initial observations were ambiguous, leaving astronomers uncertain whether it was an asteroid or a comet. Over the following weeks, follow-up observations by ground-based and space-based telescopes revealed a coma of gas and dust, confirming its identity as an active comet. The Hubble Space Telescope and the James Webb Space Telescope, JWST, provided critical insights, revealing a nucleus no larger than a kilometer and a chemical composition rich in carbon dioxide, water ice, and cyanide compounds. These findings hinted at a formation environment vastly different from the icy realms of the solar system, where comets typically contain more volatile ices like methane and ammonia. Instead, 3I Atlas appeared to have formed a colder, denser region of its home system, perhaps one with a higher concentration of carbon-rich materials. By the time 3I Atlas reached its closest approach to the Sun, on 29 October 2025, it had become a focal point for astronomers worldwide. Though it would never come closer than 1.36 AU, 23 million kilometers, between the orbits of Earth and Mars, the comet's proximity allowed scientists to study its behavior in exquisite detail. Observations from the Very Large Telescope, VLT, Chile revealed the presence of atomic nickel vapor and cyanide gas, elements rarely seen in solar system comets. These discoveries raised intriguing questions about the chemistry of interstellar space and the diversity of planetary systems across the galaxy. Was 3I Atlas's home system a mirror of our own, or had it evolved under entirely different conditions? The answers lay hidden in the data, waiting to be deciphered. One of the most astonishing revelations about 3I Atlas was its age. By tracing its trajectory back through the Milky Way, astronomers estimated that the comet had spent billions of years drifting through interstellar space before its brief encounter with the solar system. Using models of galactic dynamics and comparisons to the ages of stars the thick disk, a team led by Matthew Hopkins, July 2025, calculated that 3I Atlas was likely between 7.6 and 14 billion years old. This staggering timescale placed the comet in an era when the Milky Way was still coalescing from a primordial soup of gas and dark matter. To put this into perspective, the solar system itself is a mere 4.6 billion years old. A sprout the garden of cosmic time. 3I Atlas, by contrast, was a relic from the dawn of the galaxy, predating the formation of our own planetary system by over twice its age. Its survival through the eons was nothing short of miraculous. In the hostile vacuum of interstellar space, comets risk exposure to cosmic rays, radiation, and collisions with rogue asteroids. Yet 3I Atlas had endured, its icy nucleus preserved like a fossil of the early universe. What made this discovery even more profound was the implication that the Milky Way's thick disk was a cradle of ancient interstellar objects. The thick disk, with its warp structure and high vertical velocity, suggested a history of violent upheaval, collisions between proto-galaxies, the collapse of massive clouds, and the birth of the first stars. If 3I Atlas had originated from this region, it meant that the comet's home system had formed inches an environment vastly different from our own. Perhaps its parent star had been part of a binary system, where gravitational tugs between two stars created the perfect conditions for ejecting comets into the void. Or maybe it hailed from a now extinct stellar nursery, one of the countless nurseries that once dotted the young Milky Way. The comet's journey also highlighted the dynamic nature of the galaxy itself. The thick disk, once thought to be a static repository of old stars, was now understood to be a living, evolving structure. Its interstellar inhabitants, comets like 3I Atlas, were not just passive travelers, but active participants in the galaxy's ongoing evolution. Each interstellar object was a time capsule, carrying with it the fingerprints of its birthplace. By studying these visitors, astronomers could piece together a map of the Milky Way's history, charting the movements of stars, the mergers of galaxies, and the birth of new worlds. Yet 3I Atlas posed a paradox. Its southern origin, opposite to the direction of the sun's motion through the galaxy, defied expectations. Most models predicted that interstellar objects would originate from the solar apex, the direction inches which the sun is moving relative to nearby stars. The fact that 3I Atlas came from the opposite side suggested that the distribution of interstellar material inches the galaxy was far more complex than previously assumed. Were there unseen streams of interstellar debris flowing through the Milky Way, or did the comet's trajectory reflect a unique confluence of gravitational forces, bending its path inches ways not yet fully understood? As the comet continued its journey, its story became intertwined with humanity's own quest for knowledge. Every observation, every data point, added another thread to the tapestry of the cosmos. 3I Atlas was not just a visitor from another world, it was a reminder that the universe was a vast, interconnected web of stories, each one waiting to be told. As 3I Atlas faded from view, its legacy lingered in the data and the minds of those who had studied it. But its journey was not an isolated event. Across the Milky Way, invisible highways of interstellar debris wove through the void, carrying comets and asteroids from one corner of the galaxy to another. These cosmic highways, shaped by the gravitational tides of stars, the shockwaves of supernovae, and the unseen pull of dark matter, were the great conveyors of the universe, transporting remnants of dead stars and unborn worlds. To understand 3I Atlas's place in this grand network, astronomers needed to look beyond the comet itself. They had to trace the paths of other interstellar objects, mapping the invisible currents that guided them through the galaxy. Could these highways be mapped like the shipping lanes of Earth's oceans, revealing patterns in the distribution of interstellar material? And if so, what secrets would these maps unveil? The answer lay in the science of orbital mechanics, the precise mathematics that govern the motion of celestial bodies. By calculating the velocity vectors of interstellar objects, scientists could determine not only their origins, but also their destinations. For 3I Atlas, this meant reconstructing its entire journey from the thick disk to the solar system and beyond. But the same principles applied to every interstellar traveler, no matter how faint or distant. As the next segment begins, we turn our attention to the tools and techniques that allow astronomers to decode these cosmic pathways, from the faintest traces of a comet's coma to the subtle warping of space-time. The search for interstellar highways is a testament to humanity's unyielding curiosity. For inches the dance of comets and stars, we find not just the history of the universe, but our own place within it. In the vast, silent expanse of the cosmos, where time stretches into eons and distances defy comprehension, a traveler from another world has arrived. On July 2025, the asteroid terrestrial impact last alert system, Atlas, stationed at Rio Hurtado, Chile, captured the fleeting glow of a mysterious object streaking through the inner solar system. Dubbed 3I Atlas, this interstellar comet became the third confirmed visitor to our cosmic neighborhood, joining the enigmatic ranks of 1I Oumuamua and 2I Borisov. Its discovery marked a moment of awe and curiosity, a reminder that the universe is a dynamic tapestry of motion, where objects born inches distant stellar nurseries occasionally cross paths with our own. 3i Atlas does not belong here. Its trajectory, a hyperbolic arc curving away from the Sun, reveals its origins inches into stellar space. Moving at an astonishing 58 kilometers per second, faster than any natural object native to our solar system, it defies the gravitational pull of the stars we call home. Yet despite its speed, it poses no threat. At its closest approach to Earth, it will remain over 1.8 astronomical units, AU, away, a safe distance that allows scientists to study it without fear. Still, its presence stirs a profound question. What secrets does this ancient traveler carry from its birthplace, inches the Milky Way? As the comet hurtles toward perihelion on 29 October 2025, its icy heart will begin to warm under the sun's distant gaze, releasing a haze of gas and dust. This transformation, familiar to comets born inches the cold depths of our own solar system, hints at a shared heritage. Yet 3i Atlas is no ordinary comet. Its origin story is written inches the stars themselves. Traced backward through time, its path leads to the Milky Way's thick disk, a realm of ancient stars where the conditions for life's precursors may have once flourished. If its age estimates hold true, this comet could be a relic from an era predating the solar system itself, a time when the galaxy was young and galaxies were still forming. In this contemplative narrative, we embark on a journey alongside 3i Atlas. We will unravel the physics that govern its interstellar voyage, decode the chemistry of its icy nucleus, and ponder its cosmic origins. Through the lens of science and imagination, we will seek to understand not just the comet itself, but what it reveals about our place, inches the universe. To comprehend why 3i Atlas is an interstellar traveler, we must first understand the delicate balance of forces that dictate an object's fate, inches the solar system. Every body inches space, follows a trajectory determined by its energy relative to the Sun. For objects bound to the solar system, such as planets or long-period comets, their orbital paths are elliptical or circular, looping endlessly around the Sun. But for a rare few, the rules change. If an object's velocity exceeds the escape speed of the solar system at approximately 42.1 kilometers per second at Earth's distance from the Sun, it will not return. Instead, it will follow a hyperbolic path, an open curve that carries it forever into the void. 3i Atlas is one such object. Its hyperbolic excess velocity of 58 kilometers per second is a clear signature of its interstellar origin. This speed is not merely a number. It is a cosmic fingerprint. Unlike asteroids or comets native to the solar system, which gain their velocities from gravitational interactions with planets, 3i Atlas could not have accelerated to such speeds through collisions or planetary slingshots. Its velocity is intrinsic, a remnant of the processes that ejected it from its home system. Calculations of its orbital eccentricity, an indicator of how open a trajectory is, confirm this reality. With an eccentricity greater than 1, 3i Atlas's path is unbound, a slingshot trajectory that will eventually carry it beyond the reach of the Sun's gravity. But how do we determine where this comet came from? By tracing its hyperbolic path backward through time, astronomers reconstruct its arrival vector inches three-dimensional space. This process involves decomposing the comet's velocity into components relative to the Milky Way's galactic coordinate system: radial mass U, transverse mass volts, and vertical mass watts. 3i Atlas's radial velocity, measured at -51.0 kilometers per second, indicates it is moving away from the galactic center. Its vertical velocity of 18.5 kilometers per second indicates it is moving away from the galactic center. Its vertical velocity of 18.5 kilometers per second suggests it is ascending above the galactic plane. These measurements point to a unique origin: the thick disk of the Milky Way, a region populated by stars older than the solar system. The thick disk is a relic of the galaxy's early history, a place where stars formed inches turbulent, metal-poor environments. For 3i Atlas to hail from this region, it must be at least 7 billion years old, potentially twice the age of our own solar system. Yet the comet's journey is not purely a matter of physics. Its interstellar status is further confirmed by its trajectory's alignment with the galactic center. Unlike the previous interstellar visitors, which approached from directions closer to the solar apex, the direction inches which the Sun is moving through the galaxy, 3I Atlas, arrives from the southern celestial hemisphere. This anomaly challenges assumptions about the distribution of interstellar objects. Astronomers had predicted that most interstellar travelers would originate from the solar apex, where the density of stars is higher. The discovery of 3I Atlas suggests that our understanding of the galaxy's population of rogue comets is incomplete. Perhaps such objects are far more common than we imagined, hidden inches the shadows of distant star fields. The implications of 3I Atlas's hyperbolic escape extend beyond its own story. Its existence demonstrates that the solar system is not an isolated island, inches the cosmos. Instead, it is a participant, inches a grander cosmic exchange, one where objects are ejected from star systems and later recaptured by others. In this context, 3I Atlas is not just a visitor, it is a messenger. Its journey carries clues about the dynamics of distant planetary systems, the frequency of ejection events, and the chaotic dance of celestial bodies across the galaxy. As 3I Atlas approaches the Sun, its icy nucleus begins to transform, though the exact size of its core remains uncertain. Estimates range from 0.32 to 5.6 kilometers. Its activity is unmistakable. The Sun's radiant energy warms the comet's surface, sublimating volatile ices into gas and lofting dust into space. This process creates the coma, a glowing halo of particles that envelops the nucleus, and the tail, a stream of material pushed outward by solar radiation and magnetic fields. Yet 3I Atlas is no ordinary comet. Observations from the Hubble Space Telescope, the James Webb Space Telescope, JWST, and the Very Large Telescope, VLT, reveal a chemical profile unlike any seen inches the solar system. One of the most striking discoveries is 3I Atlas's abundance of carbon dioxide. While water ice is the dominant volatile inches most comets, this interstellar visitor carries a higher proportion of CO2, suggesting a formation environment colder than even the outer reaches of the solar system. The presence of water ice and vapor, though less prevalent, hints at a complex history. Carbon monoxide and carbonyl sulfide are also detected, their ratios offering insights into the temperatures and pressures present when the comet's materials coalesced. These compounds are not mere curiosities, they are building blocks of life, molecules that may have seeded the early Earth with the ingredients necessary for biochemistry. Even more intriguing is the detection of cyanide gas and atomic nickel vapor. These substances, observed inches concentrations similar to those found inches solar system comets, challenge the notion that interstellar objects are chemically distinct. They imply that the processes governing the formation of comets, whether inches our solar system or elsewhere, are governed by universal principles. Yet the differences inches composition, such as the elevated CO2 levels, underscore the diversity of stellar nurseries. Each interstellar object is a snapshot of a distant star-forming region, a record of the conditions that shaped its birthplace. The nucleus itself remains elusive, because the coma's light drowns out the faint glow of the nucleus. Astronomers struggle to measure its size directly. However, models based on brightness variations and thermal emissions suggest it is relatively small, likely less than 1 kilometer inches diameter. This compact size is consistent with the comet's weak outgassing, which produces a modest coma and tail. As 3I Atlas continues its journey, the Sun's influence will intensify, accelerating the release of volatiles and potentially altering its appearance. Will its activity wane as it escapes the Sun's reach, or will it fragment under the stresses of rapid heating? These questions linger, unanswered, as the comet follows its lonely path. Beyond its chemical richness, 3I Atlas offers a window into the physics of cometary evolution. The interaction between solar radiation and the nucleus's surface is a delicate ballet of energy transfer. Photons strike the comet's surface, converting kinetic energy into heat. This heat drives the sublimation of ices, creating jets of gas and dust that sculpt the coma. The resulting pressure gradients can alter the comet's rotation, causing unpredictable changes inches its trajectory. For 3I Atlas, these processes are amplified by its interstellar speed, which shortens the time it spends within the Sun's gravitational sphere of influence. Its brief encounter with the inner solar system is a fleeting performance, a cosmic encore that will soon fade into memory, yet the comet's legacy endures. The data collected by Earth-based and space-based observatories will shape our understanding of interstellar objects for decades. Already, the discovery of 3I Atlas has spurred new theories about the ejection mechanisms of comets and the distribution of volatile rich bodies inches the galaxy. Will future missions attempt to intercept such visitors, capturing samples of their alien chemistry, or will we continue to observe them from afar, content with the knowledge that we share the universe with kindred wanderers? The answers lie inches the stars, waiting to be uncovered. As 3I Atlas departs the solar system, its hyperbolic path carries it toward the unknown. Yet its journey is not merely a tale of escape, it is a chronicle of time itself. The comet's age, estimated at 7 to 14 billion years, places it among the oldest known objects inches the universe. This staggering antiquity raises profound questions. How did such an ancient body survive the tumult of cosmic history? What conditions forged its icy heart? And what secrets does it hold about the galaxy's formative years? The thick disk of the Milky Way, from which 3I Atlas originates, is a repository of the galaxy's earliest stars. These stars, born inches an era of rampant star formation, are metal poor and often surrounded by disks of gas and dust. It is within such environments that comets like 3I Atlas may have formed, their icy nuclei preserving the primordial soup of the universe. Unlike the thin disk, where younger stars like the Sun dominate, the thick disk is a dynamic, turbulent realm. Gravitational interactions between stars, supernova explosions, and the slow migration of stellar populations may have dislodged 3I Atlas from its cradle, sending it on a millennia-long voyage through interstellar space. What might this comet teach us about the conditions of its birthplace? The elevated levels of carbon dioxide and the absence of certain compounds found inches. Solar system comets suggest that 3I Atlas formed inches, a region with a different chemical equilibrium. Perhaps its parent star was smaller, or the surrounding molecular cloud was richer inches carbon-bearing molecules. Alternatively, the comet's ejection may have occurred during a period of intense dynamism, when gravitational perturbations from neighboring stars or passing molecular clouds sent debris cascading into the void. The study of 3I Atlas is not confined to its chemical composition. Its trajectory, velocity, and origin offer clues about the frequency of interstellar encounters. If comets like this are common, they may play a role inches distributing organic molecules across the galaxy, a hypothesis that resonates with the panspermia theory. Could 3I Atlas have carried the seeds of life to another world? Or might its remnants one day contribute to the emergence of life elsewhere? Such questions blur the line between science and philosophy, reminding us that the universe is not just a collection of objects, but a living, evolving entity. As 3I Atlas fades from view, its legacy endures inches the data it leaves behind. Future generations of astronomers will analyze its light, piecing together the story of its journey. They will debate its origins, its chemistry, and its significance inches the broader context of cosmic history. And as they do, they will join a lineage of curious minds who have looked to the stars and wondered, are we alone inches the universe, or are we part of a vast interconnected web of life and matter, stretching across the cosmos? The answer perhaps lies inches the next interstellar visitor. In the vast, silent expanse of the universe, comets are among the most enigmatic travelers. They're relics of a time when the cosmos was young, fragments of ice and rock that have wandered through the void for eons, carrying within them the secrets of their birthplaces. Among these celestial wanderers, 3I Atlas stands apart, not merely as a visitor from another star system, but as a messenger from a distant epoch. Discovered inches the summer of 2025 by the Atlas Survey inches Chile, this interstellar comet has captivated astronomers with its fleeting presence and its mysterious origins. As it glides through the inner solar system on a hyperbolic path, 3I Atlas reveals itself as more than a transient object. It is a frozen time capsule, a cosmic snow globe that, when warmed by the sun's light, releases a delicate mist of gas and dust. This shimmering veil, known as the coma, is a window into the primordial chemistry of its home, a world far beyond the reach of human exploration. In tracing the composition of 3I Atlas, we do not simply observe a single comet, we glimpse the raw materials of a different stellar nursery, a fragment of a story that predates the birth of our own solar system. At the heart of 3I Atlas lies its nucleus, a dense icy core that remains hidden beneath the glowing haze of its coma. This nucleus, though shrouded in uncertainty due to the overwhelming brightness of the surrounding gas and dust, is believed to span between 300 meters and 5.6 kilometers inches diameter. The exact size remains elusive, as the nucleus's light is nearly indistinguishable from the coma's luminous exhalation. Yet what is clear is the nature of this exhalation. When sunlight strikes the nucleus, it triggers a process of sublimation, wherein volatile ice is transformed directly from solid to gas, bypassing the liquid phase entirely. This transformation unleashes a cascade of molecules and particles, forming the coma and the comet's characteristic tail. The James Webb Space Telescope, JWST, has revealed that this outgassing is dominated by carbon dioxide, a substance far more prevalent in 3I Atlas than in the comets of our own solar system. Typically, comets like Halley's or 67P, Churyumov-Gerasimenko release a mix of water vapor, carbon monoxide and methane, but 3I Atlas's coma is a veritable fountain of CO2, with traces of water ice, carbon monoxide and even cyanide. The Very Large Telescope, JLT, has further uncovered the presence of atomic nickel vapor and cyanide gas, compounds that echo the volatile chemistry of certain solar system comets, but exist here in proportions that defy easy explanation. This chemical signature is not merely a curiosity, it is a clue. The abundance of carbon dioxide suggests that 3I Atlas formed in an environment far colder and more distant than the Kuiper Belt, the wellspring of many of our own comets. Such conditions are typically found in the outermost reaches of protoplanetary disks, where temperatures plummet to near absolute zero, allowing even the most volatile substances to freeze. The fact that 3I Atlas carries such a unique blend of molecules implies that its home system may have had a different evolutionary path than ours. Perhaps its parent star was smaller, its planetary architecture more chaotic, or its natal nebula enriched with materials now absent in our solar system's history. By dissecting the chemical fingerprint of 3I Atlas, scientists are not only unraveling the mysteries of a single comet, but also probing the conditions under which other star systems may have formed. The implications of 3I Atlas's chemistry extend beyond its immediate origin story. Its high concentration of carbon dioxide, for instance, raises intriguing questions about the thermal history of its birthplace. In our solar system, comets that originate from the Oort cloud, vast reservoirs of icy bodies at the edges of the solar system, tend to have lower CO2 levels compared to their Kuiper Belt counterparts. This distinction is attributed to the varying temperatures and pressures in these regions, which dictate which volatile compounds can condense and persist over billions of years. The fact that 3I Atlas's coma is so rich in CO2 suggests that it formed in a region where the temperature never rose above approximately 200 degrees Celsius, a threshold that would have allowed carbon dioxide to remain stable as ice. This turn hints at a formation zone far removed from its host star, perhaps even a binary star system or a region where gravitational perturbations scattered icy bodies into deep space. Moreover, the presence of cyanide and nickel vapor adds another layer of complexity. Cyanide, a molecule composed of carbon and nitrogen, is relatively rare in cometary comae and is often associated with high-energy processes such as shock waves or ultraviolet radiation. Its detection in 3I Atlas suggests that the comet may have experienced a brief period of intense heating, perhaps during a close encounter with its parent star or a collision with another body, before embarking on its interstellar voyage. Similarly, the presence of atomic nickel, an element that requires extreme temperatures to vaporize, indicates that the comet's internal structure may contain refractory materials. If 3I Atlas indeed carries such a diverse array of materials, it may represent a transitional class of interstellar objects, one that bridges the gap between traditional comets and more primitive asteroid-like bodies. Yet, perhaps the most profound implication of 3I Atlas's chemistry lies in its potential to challenge our understanding of the Milky Way's chemical diversity. The Milky Way is a galaxy of immense variation, with regions ranging from the metal-rich spiral arms to the metal-poor halo. The thick disk, from which 3I Atlas is believed to originate, is a particularly ancient and chemically distinct region. Stars inches the thick disk are older and contain fewer heavy elements than those inches the thin disk where the Sun resides. If 3I Atlas is indeed a native of this ancient galactic neighborhood, then its composition may reflect the primordial material from which the earliest stars and planets inches the Milky Way formed. This raises a tantalizing possibility that 3I Atlas is not just a visitor from another star system, but a relic from a time when the galaxy itself was its infancy. However, the story is not without ambiguity. While the thick disk hypothesis offers a compelling explanation for 3I Atlas's age and trajectory, some aspects of its chemical profile still puzzle researchers. For instance, the presence of water ice and carbon monoxide inches its coma suggests that it may have undergone secondary processing, perhaps inches a more recent environment, where these molecules could have been replenished or altered. Could 3I Atlas have once orbited a star inches a closer, warmer region before being ejected into the void? Or does its chemistry point to a more dynamic history, one shaped by collisions, tidal forces, or even interactions with interstellar clouds? These questions underscore the complexity of interpreting cometary data and highlight the need for continued observation and modeling. What is certain, however, is that 3I Atlas is reshaping our understanding of interstellar objects. Unlike 1I Oumuamua, which defied classification as either a comet or an asteroid, and 2I Borisov, which bore a striking resemblance to solar system comets, 3I Atlas occupies a unique niche, inches the cosmic hierarchy. Its chemical richness and unusual volatility suggest that interstellar comets may be far more diverse than previously imagined. Some may hail from the cold, dark depths of protoplanetary disks, while others could originate inches the violent aftermath of stellar explosions, or the chaotic dance of binary stars. By studying these interstellar visitors, we are not only learning about the conditions of distant star systems, but also gaining insight into the universal processes that govern the formation and evolution of comets across the galaxy. As the coma of 3I Atlas continues to glow faintly against the backdrop of the night sky, its chemical whispers carry us toward a deeper question. Where exactly inches the Milky Way did this ancient traveler originate? To answer this, astronomers have turned their gaze to the stars themselves, tracing the comet's trajectory back through the vastness of interstellar space. The clues lie not only inches the comet's velocity and path, but also inches the motion of the stars it passed, inches its long journey. By mapping the galactic coordinates of 3I Atlas's arrival, scientists hope to pinpoint the region of the Milky Way from which it hailed, a task that promises to illuminate not only the comet's origins, but also the structure and history of our galaxy. Let us now follow this thread of light and shadow, venturing into the galactic neighborhoods, where 3I Atlas may have been born, and uncovering the secrets hidden inches the stars. In the vast, dark expanse of the universe, where stars burn like distant lanterns and galaxies spiral inches silent harmony, there exists a fleeting visitor, a wanderer from the depths of interstellar space, discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS. Telescope inches Chile, 3I Atlas emerged as a transient beacon of cosmic curiosity. This enigmatic object, now designated as C2025N1, ATLAS, traverses our solar system on a hyperbolic path, its origins shrouded inches the mists of the Milky Way's ancient history. Unlike the familiar planets and asteroids bound to the Sun's gravitational embrace, 3I Atlas is a nomad, a relic of a distant stellar nursery, hurtling through the void with a velocity of 58 kilometers per second, fast enough to escape the solar system entirely. The discovery of 3I Atlas marks a pivotal moment, Inch's humanity's quest to understand the cosmos. As the third interstellar object confirmed to pass through our celestial neighborhood, it joins the ranks of 1I Oumuamua and 2I Borisov. Each a unique puzzle piece, Inches the grand tapestry of interstellar travel. Yet 3I Atlas is not merely a statistical milestone, it is a window into the primordial past. Carrying secrets of a star system billions of years removed from our own, its journey, spanning eons, invites us to ponder the interconnectedness of the universe and the possibility that life's building blocks may have traveled across the stars, long before humans gazed upward. Inches awe. As 3I Atlas approaches its closest point to the Sun on 29 October 2025, it becomes a focal point for astronomers and dreamers alike. From its icy nucleus, veiled Inches a coma of gas and dust, to its hyperbolic trajectory that defies the Sun's pull, this comet embodies the raw, untamed beauty of the cosmos. In tracing its path, we are not merely observing a distant object. We are participating in a dialogue with the universe itself, a dialogue that transcends time and space. The detection of 3I Atlas on that fateful day, July 2025, was a triumph of modern astronomy. The Atlas telescope, designed to scan the skies for potential Earth-threatening objects, captured the comet's faint glow at an apparent magnitude of 18, a ghostly whisper. Inches the night. At the time of its discovery, 3I Atlas was already 4.5 astronomical units AU from the Sun, or 670 million kilometers, and 3.5 AU from Earth, moving at a blistering speed of 61 kilometers per second. It was clear that this object was not bound to the solar system. Initial observations, however, left researchers puzzled. Was it an asteroid, a dormant rock tumbling through space, or a comet, its surface erupting Inches jets of gas and dust? The answer lay Inches the object's trajectory. While asteroids typically follow elliptical orbits, comets, especially those originating from distant star systems, travel on hyperbolic paths, their trajectories shaped by the gravitational tides of their home systems. The Atlas team quickly realized that 3I Atlas's orbit was anything but ordinary. Follow-up observations by the Zwicky Transient Facility (ZTF) and the Very Large Telescope (VLT) confirmed its interstellar origin, revealing a hyperbolic excess velocity of 58 kilometers per second relative to the Sun. This velocity, faster than any object born Inches the solar system, ruled out planetary interactions as a source of its motion. Instead, 3I Atlas had entered our cosmic backyard as a traveler from another corner of the galaxy. The collaboration between professional and amateur astronomers was critical. Inches unraveling the comet's story. Pre-discovery images from the ZTF and Atlas archives pushed back the comet's detection window to June 2025, revealing that it had passed nearly undetected due to its position near the Milky Way's dense galactic center. Here, the sky is crowded with stars, making faint objects like 3I Atlas easy to overlook. Yet, the collective efforts of the global astronomical community ensured that this cosmic interloper was not lost to obscurity. By July 2025, the International Astronomical Union's Minor Planet Center, MPC, had catalogued 3I Atlas as the third confirmed interstellar object, assigning it the designation 3I. The comet's dual identity as both a non-periodic comet, CES 2025 N1, and an interstellar visitor underscores its uniqueness. Over the following weeks, 120 observations from 31 observatories refined its orbit, confirming that it would never pose a threat to Earth. At its closest approach, it would remain 1.8 AU, nearly 70 million kilometers away, a safe distance that allowed scientists to study it without fear of impact. Yet, the true marvel of 3I Atlas lies in its composition. Unlike solar system comets, which often contain a mix of volatile ices like water and methane, 3I Atlas is unusually rich in carbon dioxide. Observations by the James Webb Space Telescope, JWST, revealed traces of water ice, water vapor, carbon monoxide, and even carbonyl sulfide compounds, that hint at a chemistry distinct from our own backyard. More intriguingly, the Very Large Telescope detected emissions of cyanide gas and atomic nickel vapor, concentrations comparable to those seen in comets from our solar system. This juxtaposition of familiarity and alien novelty raises profound questions. What processes in its parent star system forge these materials? How has this comet survived the harshness of interstellar space for eons? As 3I Atlas continues its journey, its story unfolds in real time, from its initial detection to the painstaking confirmation of its interstellar nature. Every observation adds a new chapter to humanity's understanding of the cosmos. In this dance between science and wonder, we are reminded that the universe is vast, dynamic, and full of surprises waiting to be uncovered. As 3I Atlas hurtles toward its closest approach to the Sun on 29 October 2025, its journey becomes a celestial ballet choreographed by gravity and entropy. At perihelion, the comet will pass just 1.36 AU from the Sun, between the orbits of Earth and Mars, where solar radiation will intensify its activity. The Sun's heat will sublimate the icy nucleus, releasing jets of gas and lifting dust into a glowing coma. Though 3I Atlas's nucleus remains shrouded in mystery, with estimates placing its diameter between 0.32 and 5.6 kilometers, its coma will expand, transforming the comet into a luminous spectre inches the inner solar system. Yet, despite its brilliance, 3I Atlas will remain invisible to the naked eye. Its faint magnitude of 11.5, requiring telescopes to glimpse its ethereal beauty. The comet's path through the solar system is a testament to its interstellar heritage. Unlike comets from the Oort cloud or Kuiper belt, which originate from the solar system's outer reaches, 3I Atlas arrived from the Milky Way's thick disk, a region teeming with ancient stars. This distinction is critical. The thick disk, a puffed-up layer of the galactic structure, harbors stars up to 14 billion years old, their compositions reflecting an era when the universe was young and metal-poor. By tracing 3I Atlas's trajectory, astronomers determined that it entered the solar system from the constellation Sagittarius, near the galactic center. Its velocity vector, 51 kilometers per second away from the galactic center, and 18.5 kilometers per second upward through the galactic plane, pins it to the thick disk population, a group of stars whose orbits tilt relative to the galactic plane. This connection to the thick disk carries profound implications. If 3I Atlas shares the age of its stellar neighbors, it could be at least 7 billion years old, far older than the solar system itself. Such an antiquity challenges our understanding of comet longevity. How can a fragile object endure billions of years in the vacuum of space, subjected to cosmic rays and interstellar collisions? Could 3I Atlas's survival hint at mechanisms that shield comets from destruction, such as protective layers of ice, or a fortuitous orbital history? Alternatively, its age might suggest that comets like 3I Atlas are relatively common in the galaxy, their numbers yet to be fully quantified. The comet's chemical fingerprint further complicates these questions. While the presence of carbon dioxide and water ice aligns with solar system comets, the absence of ammonia, a compound abundant in our own icy bodies, hints at a different formation environment. Perhaps 3I Atlas's parent star system experienced a colder, drier protoplanetary disk, or its materials were processed under unique conditions. The detection of cyanide and nickel vapor, meanwhile, suggests that its nucleus contains refractory compounds resistant to sublimation, preserving relics of its birthplace. These clues invite speculation about the diversity of planetary systems beyond our own, and the universality of comet-forming processes. As 3I Atlas prepares to depart the solar system, its fate is sealed. After perihelion, it will recede from the Sun, its trajectory carrying it back into the galactic abyss. By December 2025, it will fade into obscurity, its solar elongation increasing as it moves beyond the reach of even the most powerful telescopes. Yet, its legacy endures inches the data it leaves behind. Every observation, every spectral line, every image adds to a growing archive of interstellar visitors. Each one a thread inches the cosmic web that binds the stars together. The study of 3I Atlas's origin has sparked a renaissance in astrophysical inquiry, particularly regarding the structure and evolution of the Milky Way. Its placement in the thick disk, a population of stars that predates the thin disk, has forced astronomers to reconsider the distribution of interstellar objects across the galaxy. Traditionally, models predicted that most interstellar visitors would hail from the solar apex, the direction of the sun's motion through the galaxy. However, 3I Atlas's southern origin challenges this assumption, suggesting that interstellar objects may arrive from all directions, their trajectories shaped by the complex gravitational dynamics of the Milky Way. This revelation has ignited debates among scientists. Is 3I Atlas a statistical outlier, a rare artifact of a chance encounter? Or does its southern origin indicate that thick disk comets are more prevalent than previously thought? The answer may lie in the ongoing search for more interstellar objects, a task complicated by the difficulty of detecting faint bodies against the crowded backdrop of the galactic center. Future surveys, equipped with larger telescopes and advanced algorithms, may uncover a hidden population of interstellar comets, each bearing the imprint of its native star system. Moreover, 3I Atlas's age, a subject of contention between two competing studies, raises fundamental questions about the stability of comets over cosmic timescales. The first study, led by Matthew Hopkins, estimated the comet to be between 7.6 and 14 billion years old, older than the solar system. Another analysis by Asta Taylor and Darrell Seligman placed its age between 3 and 11 billion years, overlapping with the thick disk's typical stellar population. These discrepancies highlight the uncertainties inherent in extrapolating galactic dynamics to individual objects, yet they also underscore the potential of 3I Atlas to refine our understanding of galactic structure and the lifetimes of small bodies in interstellar space. As we turn our gaze to the next segment, stellar neighborhoods, thick disk versus thin disk, we find ourselves at the threshold of a deeper exploration. The thick disk, with its ancient stars and tilted orbits, offers a stark contrast to the thin disk's youthful vibrancy. Understanding this dichotomy is key to deciphering 3I Atlas's origins and the broader story of our galaxy's evolution. In the coming chapters, we will unravel the mysteries of these stellar neighborhoods, peeling back the layers of the Milky Way to reveal the cosmic forces that have shaped its inhabitants for billions of years. In the vast, silent expanse of the cosmos, where time stretches beyond human comprehension, a single interstellar visitor has ignited a debate that echoes through the halls of astrophysics. 3I Atlas, a comet born of another star's cradle, now dances through our solar system, carrying secrets etched in the annals of cosmic history. Yet, even as it passes, its age, a seemingly simple number, has become a battleground of ideas. Two teams of scientists, armed with data and theory, have reached divergent conclusions. One claims the comet is over 7 billion years old, a relic from the Milky Way's youth. The other argues for a younger lineage, a mere 3 billion years. How can the same object, hurtling through space on a hyperbolic arc, bear such contrasting tales of time? The answer lies not in the comet itself, but in the assumptions we make about the universe's past and the limitations of our ability to reconstruct it. This is the story of 3I Atlas, a celestial wanderer caught in the crossfire of cosmic chronology, and the profound implications of its age for our understanding of the stars. To unravel the mystery of 3I Atlas's age, we must first understand how astronomers measure time in the universe. Unlike the steady tick of a clock, cosmic timelines are built on indirect evidence, pieced together from the motion of stars, the composition of interstellar bodies, and the remnants of ancient collisions. For 3I Atlas, the key lies in its trajectory and velocity, which act as a cosmic fingerprint of its origin. Matthew Hopkins and his team anchored their conclusion to the comet's vertical velocity, its motion perpendicular to the galactic plane. Using the galactic coordinate system, they found that 3I Atlas was moving upward through the Milky Way at 18.5 kilometers per second, a speed far higher than most nearby stars. This vertical velocity, they argued, places the comet among the thick disk population of stars, a group known to be ancient, formed billions of years ago when the Milky Way was still a chaotic, youthful galaxy. By linking 3I Atlas to the typical ages of thick disk stars, estimated at 7.6 to 14 billion years, they posited that the comet itself must share this antiquity. To them, 3I Atlas is a time capsule, a fragment of the Milky Way's earliest epochs. Conversely, Asta Taylor and Darrell Seligman approached the problem through a different lens. They questioned whether the comet's vertical velocity alone was sufficient to assign it to the thick disk. Instead, they turned to dynamical simulations, computer models that traced the paths of objects through the galaxy over eons. Their analysis revealed that while 3I Atlas's trajectory does suggest an extragalactic origin, its velocity vector could also be explained by interactions within the thin disk, a younger, denser population of stars. Moreover, they highlighted potential biases Inch's stellar age estimates, noting that uncertainties Inch's the thick disk star formation history could skew results. By incorporating these factors, Taylor and Seligman proposed a narrower age range, 3 to 11 billion years. Their model allowed for a more recent ejection from a star system, possibly due to gravitational perturbations. Inch is a dynamically unstable region of the galaxy. The disparity between these conclusions hinges on a critical assumption: the relationship between a comet's motion and its birthplace. For Hopkins et al., the vertical velocity is a definitive marker of the thick disk. For Taylor and Seligman, it is one piece of a complex puzzle that includes the comet's orbital tilt, gravitational influences, and the likelihood of observational biases. Both teams operate within the boundaries of current knowledge, yet their differing interpretations underscore a deeper truth. Our understanding of the cosmos is always provisional, shaped by the tools and theories of our era. The age of 3I Atlas is more than a numerical disagreement. It is a portal into the Milky Way's hidden history. If the comet is indeed 7 billion years old, it predates the solar system by over 2 billion years, a staggering span that bridges the gap between the galaxy's violent youth and its present-day tranquility. In this scenario, 3I Atlas originates from the Milky Way's thick disk, a region where stars formed Inch's bursts of starbirth, triggered by ancient mergers and gravitational tides. Its high vertical velocity suggests it has spent eons oscillating above and below the galactic plane, a lonely traveler untouched by the ordered motions of younger stars. Such an object would be a relic of the galaxy's infancy, carrying chemical signatures from an era when the cosmos was still rich in Inch's primordial elements and devoid of the heavy metals forged Inch's later supernovae. Studying 3I Atlas under this hypothesis could offer unprecedented insights into the Milky Way's early chemistry, revealing how the first generations of stars sculpted their environment. Yet if the comet is younger, say 3 billion years, its origin story shifts dramatically. AMPA's 3 billion-year-old 3I Atlas could have been ejected from a star system, Inch's the thin disk, a region where star formation continues to this day. Such an ejection might occur Inch's a dense stellar nursery, where gravitational interactions between young stars or massive planets could hurl comets into interstellar space. Alternatively, the comet could hail from a disrupted star cluster, where tidal forces tore apart a tightly bound group of stars, scattering their debris into the galactic void. In this case, 3I Atlas is not a relic of the past, but a product of ongoing cosmic churn, a testament to the dynamic, ever-changing nature of the Milky Way. This interpretation aligns with recent discoveries of interstellar objects originating from the thin disk, suggesting that such events may be more common than previously thought. The implications of these scenarios extend far beyond 3I Atlas itself. The comet's age determines whether it represents a rare artifact from the galaxy's youth or a recurring phenomenon. Inches its evolutionary cycle. If older, it challenges our understanding of the thick disk's role, Inches shaping the Milky Way, potentially redefining how we model the distribution of dark matter or the frequency of ancient star systems. If younger, it reinforces the idea that interstellar comets are a natural byproduct of stellar dynamics, hinting at a hidden reservoir of such objects waiting to be discovered. Either way, 3I Atlas serves as a Rosetta Stone for decoding the Milky Way's past, offering clues about the processes that govern star formation, planetary migration, and the long-term stability of galaxies. Moreover, the comet's age speaks to the broader question of life inches the universe. If 3I Atlas carries organic molecules or prebiotic compounds from a time before the solar system, it could provide a window into the raw materials available for life's emergence elsewhere. Conversely, a younger origin might suggest that such materials are continuously replenished through stellar interactions, increasing the likelihood of life arising in diverse environments. In either case, the comet reminds us that the universe is a vast repository of stories, each object a chapter, inches a narrative stretching back to the dawn of time. To resolve the age divide, scientists must turn to the tools that allow them to peer into the cosmos's depth. Telescopes like the Hubble and James Webb, which dissect the light of 3I Atlas for chemical fingerprints, are essential. Spectroscopy, the art of analyzing light to determine composition, reveals the presence of carbon dioxide, water ice and cyanide, clues that may hint at the comet's birthplace. Meanwhile, astrometry, the precise measurement of position and motion, refines the comet's trajectory, narrowing its possible origins. Computational models, too, play a role, simulating the galaxy's gravitational landscape to map the comet's journey backward inches time. Yet, even with these tools, uncertainty lingers. The age of 3I Atlas is not a fixed truth but a hypothesis, a fragile bridge between data and interpretation. As we refine our instruments and expand our theoretical frameworks, we edge closer to an answer, but the journey itself is as enlightening as the destination. For inches the search for cosmic time, we confront the limits of our knowledge and the infinite mysteries of the universe. This script balances scientific rigor with poetic reflection, weaving the technical details of 3I Atlas into a narrative that contemplates humanity's place in the cosmos. Each section builds upon the last, guiding the reader from the comet's discovery to the philosophical implications of its age, while maintaining a tone of awe and curiosity. In the vast, silent expanse of the cosmos, where time stretches into eons and distances defy comprehension, humanity has long sought to decipher the universe's secrets. Among the most enigmatic of these secrets are interstellar visitors, objects born inches distant star systems, ejected into the void, and now drifting through the Milky Way as relics of ancient epochs. 3I Atlas, the third such interstellar comet ever discovered, is one such traveler. Its arrival inches our solar system, 2025, ignited a wave of scientific curiosity, not merely because it hails from beyond our planetary neighborhood, but because it carries within its icy nucleus the fingerprints of a time predating the birth of the sun. To understand 3I Atlas's origins and age is to peer into the deep past of the galaxy itself, a task akin to unearthing a fossilized meteorite from the primordial chaos of the cosmos. Astronomers, inches this pursuit, become cosmic archaeologists. They wield telescopes as their brushes, spectrographs as their chisels, and orbital mechanics as their excavation tools. The challenge is immense. How does one determine the age of an object that has spent billions of years adrift inches into stellar space? How does one trace its trajectory back to the cradle of its birth, when the galaxy itself has shifted and evolved over time? The answer lies inches the stars themselves. By mapping 3I Atlas's hyperbolic path and analyzing its velocity components, scientists have begun to unravel a story that stretches far beyond our solar system. A story written inches the motions of ancient stellar populations and the gravitational tides of the Milky Way. Yet, this endeavor is not without its uncertainties. The galaxy is a dynamic place, shaped by collisions, mergers, and the slow churn of cosmic evolution. The assumptions we make about its history must be tested against the evidence left inches the paths of interstellar travelers like 3I Atlas. As we delve deeper into the science of stellar archaeology, we find ourselves at the intersection of astrophysics and paleontology, where every observation is a clue, and every calculation a step toward reconstructing the universe's hidden past. To determine the age and origin of 3I Atlas, astronomers rely on a combination of orbital dynamics and stellar population analysis. The comet's trajectory, characterized by a hyperbolic excess velocity of 58 kilometers per second relative to the Sun, immediately signaled its interstellar nature. Unlike objects bound to the solar system, which follow elliptical orbits and exhibit velocities constrained by the sun's gravity, 3I Atlas's path is unbound, a cosmic slingshot hurled from some distant stellar nursery. By tracing this trajectory backward through the galaxy, scientists identified the comet's point of origin inches the direction of the constellation Sagittarius, near the Milky Way's galactic center. However, pinpointing the exact age of 3I Atlas required a deeper dive into its motion. In galactic coordinates, an object's velocity can be decomposed into three components. U, the radial velocity toward or away from the galactic center. Volts, the tangential velocity inches the direction of the galaxy's rotation. And watts, the vertical velocity above or below the galactic plane. For 3I Atlas, these components revealed a critical insight. Its vertical velocity, watts, 118.5 kilometers per second, was significantly higher than the average for nearby stars. This upward motion places the comet inches a distinct category, objects belonging to the Milky Way's thick disk. The thick disk is a population of stars and interstellar material that predates the galaxy's thin disk, where the majority of stars, including our Sun, reside. Thick disk stars are older, formed in an era when the Milky Way was still coalescing from primordial gas clouds. Their chemical compositions, marked by lower abundances of heavy elements, metals, reflect the conditions of an earlier galactic epoch. By associating 3I Atlas with this population, astronomers inferred that the comet likely shares their antiquity. Further support came from statistical analysis of stellar motion patterns. Studies by teams such as those led by Matthew Hopkins and Asta Taylor utilized simulations of the Milky Way's structure to model the likelihood of 3I Atlas originating from the thick disk. By comparing the comet's velocity vector to the kinematic properties of thick disk stars, they estimated its age to be between 7.6 and 14 billion years, a span that deadwoods the 4.6 billion year history of the solar system. Independent analyses, such as those by Darrell Seligman, corroborated these findings, suggesting a slightly narrower range of 3 to 11 billion years. Together, these studies painted a picture of 3I Atlas as a relic from the early days of the Milky Way, a time when the galaxy was still forming and its stars were young. Yet, this conclusion hinges on a critical assumption that the Milky Way's structure and stellar populations have remained relatively stable over such vast timescales. In reality, the galaxy is a dynamic entity, shaped by mergers with smaller galaxies, the gravitational tides of dark matter, and the chaotic dance of star formation. These processes can alter the trajectories of interstellar objects, making precise age estimates a complex puzzle. Still, the alignment of 3I Atlas's motion with the thick disk provides a compelling starting point, one that invites further scrutiny as new data emerges. While the association of 3I Atlas with the thick disk offers a plausible explanation for its age, it also raises profound questions about the nature of interstellar objects and the history of the Milky Way. One of the most striking aspects of 3I Atlas is its origin inches the southern celestial hemisphere, a region that contradicts earlier predictions about where interstellar visitors would most commonly originate. Previous models suggested that interstellar objects would predominantly arrive from the solar apex, the direction inches which the sun is moving relative to local stars, located inches the northern sky. The fact that 3I Atlas emerged from the opposite quadrant challenges these assumptions, hinting that our understanding of the galaxy's stellar dynamics may be incomplete. This anomaly could stem from several possibilities. Perhaps the Milky Way's thick disk is more asymmetrically distributed than once believed, with a higher concentration of older stars inches the southern regions. Alternatively, the galaxy's gravitational interactions with neighboring structures, such as the Magellanic Clouds or the Gaia Sausage, a remnant of a dwarf galaxy devoured by the Milky Way, may have perturbed the trajectories of interstellar objects, scattering them inches unexpected directions. Either scenario suggests that the Milky Way is a more turbulent and heterogeneous environment than previously modeled, with implications for how interstellar objects are distributed and detected. Moreover, the high vertical velocity of 3I Atlas underscores the importance of considering three-dimensional motion When studying galactic dynamics, most telescopic surveys are optimized for objects inches the galactic plane, where the density of stars and interstellar material is highest. Interstellar objects like 3I Atlas, however, travel along inclined or even perpendicular paths, making them harder to detect until they cross the plane. This observational bias may mean that many interstellar visitors go unnoticed, especially those originating from the thick disk or halo. Future surveys, such as those conducted by the Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, aim to address this gap by scanning the entire sky with unprecedented sensitivity, potentially uncovering a wealth of interstellar objects that have eluded detection thus far. The implications of 3I Atlas's age extend beyond its immediate origins. If the comet truly predates the solar system by billions of years, it serves as a direct witness to the conditions of the early galaxy. Its composition, as revealed by observations from the James Webb Space Telescope and the Very Large Telescope, includes volatile compounds such as carbon dioxide, water ice, and cyanide substances that may have played a role in seeding the chemical complexity necessary for life. By studying these materials, scientists can piece together the evolutionary pathways of planetary systems, comparing the building blocks of our own solar system to those of distant worlds. Yet the study of interstellar comets is still in its infancy. While 3I Atlas provides a rare opportunity to examine an object from another star system, it is only one data point in a much broader cosmic census. The discovery of more interstellar visitors, coupled with advances in computational modeling and observational technology, will be crucial for refining our understanding of galactic history. For now, 3I Atlas remains a testament to the power of interdisciplinary research, bridging the fields of planetary science, galactic astronomy, and astrochemistry to illuminate the connections between stars, planets, and the vast interstellar medium that binds them. As we contemplate the origins and age of 3I Atlas, it becomes evident that this comet is more than a fleeting guest. Inches the solar system. It is a messenger from the distant past, carrying the legacy of a galaxy inches flux. Its hyperbolic trajectory, its association with the thick disk, and its ancient age all serve as pieces of a larger puzzle, one that demands a deeper exploration of the comet's motion through space. Just as archaeologists follow the clues left in fossilized bones to reconstruct the lives of extinct species, astronomers must trace the path of 3I Atlas through the gravitational tides of the Milky Way to understand its journey. In the next segment, we will turn our attention to the comet's orbital dynamics, examining how its velocity and direction relate to the forces that govern the galaxy. By mapping its trajectory in 3 dimensions, we will uncover the cosmic highways and gravitational bottlenecks that have shaped its voyage across interstellar space. This analysis will not only refine our understanding of 3I Atlas's origin, but also shed light on the mechanisms that eject comets from their native systems and scatter them into the void. Through this lens, we will see how the Milky Way itself acts as a cosmic conveyor belt, ferrying these ancient travelers across the galaxy and delivering them, like stardust on a cosmic wind, to the doorstep of our solar system. Word count, not 1,500. Each section can be expanded further to meet the 3,000-word target by elaborating on specific studies, adding historical context to the discovery of interstellar objects, and exploring the philosophical implications of cosmic archaeology. In the boundless expanse of the Milky Way, where stars flicker like distant campfires and galaxies swirl in silent symphony, a solitary traveler arrived. On 1 July 2025, the asteroid terrestrial impact last alert system, ATLAS, stationed in Rio Hurtado, Chile, captured the first glimpse of an object unlike any seen before. Designated initially as A11PEL3Z, this interstellar comet, later named 3I Atlas, was not born in the solar system, but hailed from the far reaches of the galaxy. Its discovery marked a pivotal moment in astronomy, echoing the first whispers of interstellar visitors, 1I Oumuamua and 2I Borisov. Yet 3I Atlas carried a tale even older and stranger. When it entered the inner solar system, 3I Atlas was already a wanderer, hurtling at 58 kilometers per second, relative to the Sun, a velocity too great to be explained by the gravitational dance of our planetary neighborhood. Its path, a hyperbolic arc, revealed an object unshackled by the Sun's pull, destined to return to the void from which it came. For astronomers, this was both a puzzle and a promise, a chance to peer beyond the confines of our stellar cradle into the vast enigmatic depths of interstellar space. What lay ahead was not merely the study of a comet, but a window into the ancient architecture of the Milky Way itself. As telescopes turned their gaze toward 3I Atlas, scientists sought to unravel its secrets, its origins, its age, and the cosmic forces that shaped its journey. In doing so, humanity was reminded of its place in the cosmos, not as masters of the universe, but as curious observers, piecing together the story of existence one star, one comet, and one galaxy at a time. To understand 3I Atlas is to grasp the delicate balance of motion and gravity that governs the universe. The comet's hyperbolic trajectory, a defining feature of its identity, speaks volumes about its interstellar provenance. Unlike the elliptical orbits of most solar system objects, which loop endlessly under the Sun's influence, a hyperbola represents an escape. The comet's velocity, exceeding the solar system's escape velocity, confirmed that it was not native to this realm. No planetary encounter had accelerated it to such speeds. Instead, its motion was intrinsic to its birthplace, a testament to the turbulent forces of its stellar nursery. The Atlas system, designed to detect potential Earth-threatening asteroids, became an unlikely herald of this interstellar visitor. When A11 Palaeo 3Z was first flagged, its position and velocity defied easy classification. Located 4.5 astronomical units, AU, from the Sun, it was already a ghostly presence, its faint glow lost among the crowded stars of the galactic center. Yet, follow-up observations from global observatories, including the Zwicky Transient Facility and the Hubble Space Telescope, revealed a critical truth. This was no ordinary solar system object. Its path curved sharply under the Sun's gravity, but it would not be ensnared. Instead, it would swing past the inner solar system and vanish once more into the interstellar abyss. The comet's nucleus, shrouded in mystery, posed another challenge. Unlike asteroids, which reflect sunlight off solid surfaces, comets are volatile worlds. As 3I Atlas neared the Sun, heat sublimated its frozen ices, releasing gas and dust that formed a glowing coma. This veil obscured the nucleus, making direct measurements impossible. However, indirect methods offered clues. Hubble's sharp vision suggested a nucleus no larger than 1 kilometer diameter, while the James Webb Space Telescope detected an unusual chemical signature, carbon dioxide dominating over water ice, alongside traces of carbon monoxide, carbonyl sulfide, and even cyanide. Such a composition hinted at an origin in a cold, distant environment, far removed from the warmer, water-rich regions of the solar system. Yet the comet's most profound secret lay in its journey. By tracing its path backward through space-time, astronomers uncovered a trail stretching across billions of years. The Milky Way's thick disk, the ancient metal-poor halo of stars, emerged as the likely birthplace. Here, a realm older than the solar system itself, 3I Atlas had been sculpted by the gravitational tides of neighboring stars and the slow churn of galactic evolution. Its high vertical velocity relative to the galactic plane further reinforced this connection, placing it among the relics of an era when the Milky Way was younger and less structured. The implications of 3I Atlas's origin are staggering. If estimates hold true, that it is between 7.6 and 14 billion years old. This comet predates the solar system by eons. To comprehend its age is to grasp the vast timescales of galactic history. While our Sun formed 4.6 billion years ago, 3I Atlas may have emerged during the Milky Way's earliest days, when the first stars ignited and galaxies collided in fiery spectacles. Its journey since then has been one of isolation, a lonely pilgrimage through a galaxy that has changed dramatically in its absence. This comet is not merely a wanderer. It is a relic, a time capsule carrying the chemical imprints of its primordial home. The abundance of carbon dioxide in its coma for instance, suggests an origin. Inch is a cold, dark region where volatile compounds froze solid. Such conditions are rare. Inch is the solar system, where the sun's warmth prevents the widespread accumulation of CO2. Yet, Inch is the thick disk, where temperatures are frigid and starlight weak. Such ices could persist for billions of years. By studying 3I Atlas, scientists hope to reconstruct the environmental conditions of a long-lost stellar cradle, one that may have resembled the early Milky Way before the formation of modern star systems. The comet's trajectory also offers insights into the galaxy's gravitational architecture. Unlike 1I Oumuamua and 2I Borisov, which approached from directions aligned with the sun's motion through the galaxy, 3I Atlas originated from the southern celestial hemisphere, an unexpected find. Theories about interstellar object origins had predicted a bias toward the solar apex, the direction inches which the sun travels relative to local stars. The fact that 3I Atlas defies this expectation raises intriguing questions. Is it a statistical outlier, or does it signal a hidden population of interstellar objects arriving from the galaxy's uncharted depths? If the latter, it could mean that the Milky Way is far more dynamic and interconnected than previously imagined, with gravitational interactions between stars and stellar clusters frequently ejecting comets like 3I Atlas into the interstellar void. Furthermore, 3I Atlas's journey hints at a possible connection to now destroyed satellite galaxies. The Milky Way's thick disk is believed to have formed inches part through mergers with smaller galaxies, their remnants scattered like stardust across the galactic plane. If 3I Atlas hails from such a progenitor, its survival as a coherent body despite the violent processes of galactic evolution is a testament to its resilience. Alternatively, it may have cycled through multiple star systems, each encounter nudging it closer to the Milky Way's center before finally casting it toward the solar system. Either scenario paints a picture of a galaxy teeming with motion and transformation, where the destinies of comets and stars are intertwined. Yet perhaps the most profound implication of 3I Atlas lies in its role as a cosmic probe. Every interstellar object that traverses the solar system carries information about its birthplace, offering a rare opportunity to study the chemistry and dynamics of distant star systems. With 3I Atlas's rich inventory of volatile compounds and its ancient age, astronomers have a unique chance to test theories about the formation of planetary systems. Does the presence of carbon dioxide suggest a different pathway for comet formation? Inch is the early galaxy. Could its chemical composition inform models of how life's building blocks might have been delivered to nascent worlds? These questions, though speculative, underscore the comet's value as a bridge between the familiar and the unknown. As 3I Atlas continues its celestial voyage, its path brings it ever closer to the sun, a fleeting encounter that will shape both its fate and our understanding of the cosmos. From its distant origins, inches the Milky Way's thick disk, to its brief sojourn, inches the inner solar system. This comet's journey is a microcosm of the universe's grand design, a story of motion, transformation, and the relentless passage of time. What will happen as it crosses the threshold of the sun's domain? How will its fragile structure respond to the searing heat and radiation of our nearest star? And what new secrets will it unveil as it dances through the heliosphere? These are the questions that await us as we turn our gaze toward the next chapter of 3I Atlas's saga. In the coming weeks, as the comet approaches perihelion, its luminous coma will expand, and its chemical emissions will intensify. Observatories on Earth and inches space will track its every movement, seeking to decode the messages it carries from the depths of interstellar space. But for now, let us step back and consider the broader context of this encounter. In tracing 3I Atlas's path from the galactic center to the sun, we are not merely witnessing the passage of a single comet. We are glimpsing the intricate web of forces that bind the Milky Way together, the gravitational tides, the stellar migrations, and the ancient collisions that have shaped our galaxy over billions of years. Through 3I Atlas, we are reminded that the universe is not a static tapestry, but a living, evolving entity, where every object, no matter how small, plays a role. Inches the cosmic narrative. As the comet draws nearer, so too does our sense of wonder. In the vastness of space, where time stretches into epochs and distances defy comprehension, 3i Atlas stands as a symbol of our enduring quest to understand the cosmos. It is a reminder that the universe is full of surprises, waiting patiently to be discovered by those who dare to look. And as we prepare to witness its final act, we are left with a humbling realization. Inch is the grand theater of the stars. We are both audience and actor, forever seeking to unravel the mysteries of our existence. The universe is a tapestry of motion, where objects drift through the void on paths shaped by gravity, time, and chance. Among these wanderers, interstellar travelers stand apart, rare, enigmatic emissaries from distant stars, their trajectories defying the quiet order of our own cosmic neighborhood. In July 2025, humanity's gaze turned toward one such visitor. 3i Atlas, a comet born inches the shadow of the Milky Way's ancient thick disk. Unlike the countless asteroids and comets that circle the Sun inches predictable cycles, 3i Atlas was not bound by the gravitational embrace of our star. Instead, it hurtled inward on a hyperbolic path. A fleeting guest inches the solar system, destined to vanish into the dark once more. Its arrival marked a rare opportunity, a window into the chemistry, history, and dynamics of a cosmos far beyond the familiar. As scientists tracked its progress, they marveled at the paradox of its existence. A relic older than our own planetary system, forged inches the crucible of another star's birth, now traversing a region of space where Earth itself is but a transient speck. The solar system is a sanctuary of stability, a realm where the sun's gravity weaves a delicate dance of orbits. Yet even here, the occasional interstellar interloper disrupts the equilibrium. Before 3i Atlas, only 2 such visitors had ever been confirmed. 1i Oumuamua, the mysterious cigar-shaped object that baffled astronomers inches 2017. Now, with 3i Atlas, a third chapter inches this cosmic story unfolded. Its approach brought not only scientific curiosity, but a profound sense of wonder, the realization that the cosmos is not a silent expanse, but a living, interconnected web of motion and memory. As 3i Atlas neared perihelion, the closest point to the Sun, its icy nucleus began to awaken, releasing plumes of gas and dust inches a final fleeting act of self-expression. This moment, brief and brilliant, became a testament to the universe's capacity for surprise, a reminder that even inches the vastness of space, every object carries a secret waiting to be uncovered. On 29 October 2025, 3i Atlas reached perihelion, its closest approach to the Sun at a distance of 1.36 astronomical units, AU, between the orbits of Earth and Mars. Though this might seem relatively far, it was enough to trigger the comet's transformation from a frozen traveler into an active celestial body. As the Sun's rays bathed its surface, heat sublimated volatile ices, locked within its nucleus, converting them directly from solid to gas. This process, known as outgassing, released a cascade of molecules into the surrounding space, forming a glowing coma, a tenuous envelope of gas and dust that extended for thousands of kilometers. Jets of material, propelled by the pressure of escaping gases, sculpted the coma into an irregular shape, while finer particles drifted outward, trailing behind the nucleus like a whispery veil. Observing this spectacle required the combined efforts of some of humanity's most advanced instruments. The Hubble Space Telescope, with its unparalleled resolution, captured images of 3i Atlas's coma and nucleus, revealing a dynamic interplay between the comet's internal structure and external forces. Meanwhile, the James Webb Space Telescope, JWST, sensitive to infrared wavelengths, probed deeper into the chemical composition of the outgassed material. What it found was extraordinary: an abundance of carbon dioxide, alongside traces of water ice, carbon monoxide, and carbonyl sulfide. These findings hinted at a formation history unlike any seen inches the solar system's native comets, which typically contain higher proportions of water and simpler organic compounds. The presence of carbon dioxide suggested that 3i Atlas had formed inches a colder, more distant environment, possibly inches the outer reaches of its home star's protoplanetary disk. Ground-based telescopes, such as the Very Large Telescopes, VLT, inches Chile, added further layers to this portrait. Spectroscopic analysis revealed the presence of cyanide gas and atomic nickel vapor, substances rarely detected inches cometary emissions. These discoveries raised intriguing questions about the conditions under which 3I Atlas originated. Could its parent star have hosted a different suite of chemical reactions? Or did the comet's journey through interstellar space expose it to unique radiation or magnetic fields? Each observation peeled back a new layer of mystery, painting a picture of a comet that was both alien and familiar, a bridge between the solar system and the wider galaxy. Even as 3I Atlas passed its closest point to the Sun, its visibility from Earth remained elusive, with a peak apparent magnitude of only 11.7. It was too faint to be seen without powerful telescopes. Yet this limitation proved a boon for robotic missions. Mars orbiters, positioned inches the same orbital plane as the comet's trajectory, had a vantage point unobstructed by the glare of the Sun. From the red planet, they captured images of 3I Atlas at its brightest, moments when the comet's coma glowed against the Martian sky. These observations, relayed across millions of kilometers, offered a perspective no human had ever experienced, a view of an interstellar traveler from another world. The data gathered during 3I Atlas's flyby challenged existing models of interstellar objects and their behavior. One of the most striking revelations came from the comet's brightness, or rather the lack thereof. Despite its rich carbon dioxide content, which should have driven intense outgassing and a correspondingly luminous coma, 3I Atlas appeared relatively dim. This discrepancy forced scientists to reconsider the efficiency of sublimation processes inches such ancient bodies. Perhaps the comet's surface had been shielded for eons by a crust of non-volatile materials, limiting the exposure of fresh ices to solar radiation. Alternatively, its age, estimated at 7 to 14 billion years, might have allowed volatile compounds to escape over time, leaving behind a nucleus with fewer active regions. Either way, the findings underscored the complexity of interstellar comets, which defy simplistic assumptions about their origins and evolution. Beyond its chemical makeup, 3I Atlas's trajectory held clues to the architecture of the Milky Way. Tracing its path backward revealed that it hailed from the galaxy's thick disk, a region populated by older stars with lower metallicity than the Sun. This origin stood in stark contrast to the previous interstellar visitors, which had emerged from the thin disk or the galactic halo. The thick disk's tilted orientation meant that 3I Atlas approached the solar system from a direction nearly perpendicular to the plane of the Milky Way, a trajectory that had never been observed inches an interstellar object before. Such a path implied that the thick disk, long considered a stable reservoir of ancient stars, might also harbor a hidden population of comets and asteroids, remnants of planetary systems long since dissolved. Perhaps the most profound implication of 3I Atlas's journey lay inches its age. At 7 to 14 billion years old, it predated the solar system by nearly 3 billion years. This made it not just a relic, but a witness to the early history of the galaxy itself. If such objects are common inches the interstellar medium, they could serve as time capsules, preserving the conditions of their formation environments. Studying them might reveal how planetary systems evolve over cosmic timescales, offering insights into the birth of stars and the distribution of life's building blocks across the galaxy. Moreover, the discovery of 3I Atlas hinted at the possibility of future missions to interstellar visitors directly. While current technology limits our ability to send probes to such distant targets, advances in propulsion and autonomous navigation could one day allow us to follow these wanderers to their homes, unraveling the secrets of the cosmos at its most fundamental level. For all its scientific promise, 3I Atlas remained a ghostly presence, inches the night sky, elusive even to the most sophisticated instruments. Its faintness, coupled with its position near the dense star fields of the galactic center, posed significant challenges for observers. The crowded backdrop of the Milky Way's core, where millions of stars blurred together, made it difficult to distinguish the comet from its stellar neighbors. Even the automated algorithms, designed to detect moving objects, struggled to isolate 3I Atlas, requiring painstaking manual verification by astronomers. This struggle highlighted a sobering truth. Inches the vastness of the universe, Even the most extraordinary phenomena can remain hidden inches plain sight. Yet the obstacles faced by 3i Atlas's discoverers were not merely technical, they were existential. The comet's southern origin, opposite to the sun's motion through the galaxy, had defied expectations. Astronomers had assumed that most interstellar objects would hail from the solar apex, the direction inches which the sun travels relative to neighboring stars. The fact that 3i Atlas came from the opposite hemisphere suggested either a statistical anomaly or a fundamental misunderstanding of the galactic distribution of such objects. As telescopes turned their gaze southward inches the coming decades, the search for more interstellar visitors would take on new urgency, reshaping our map of the cosmos. But first, the story of 3i Atlas demanded a deeper look at the tools and techniques that had made its discovery possible. How had a faint, fast-moving comet slipped through the cracks of the Atlas survey? What role had amateur astronomers played inches piecing together its pre-discovery observations? And why had the Galactic Center's starry maelstrom obscured its path for so long? These questions, and the answers that followed, would illuminate not only the nature of interstellar comets, but the very limits of human perception inches the universe. To understand 3i Atlas fully, one had to confront the challenges that had hidden it, and the ingenuity that had finally brought it to light. Introduction, 400 words, framed 3i Atlas as a cosmic enigma, emphasizing its rarity and significance. Man's explanation, 800 words, detailed the perihelion event, observations by Hubble, JWST and VLT, and the comet's chemical uniqueness. Man's exploration, 1,000 words, analyzed implications for interstellar object theory, galactic structure, and the potential for future missions. Transition, 800 words, highlighted observational challenges, statistical anomalies, and the broader quest to understand interstellar visitors. In the vast glittering tapestry of the night sky, there exist regions where even the sharpest human gaze falters. The galactic center, a swirling nexus of billions of stars, is one such place, a celestial labyrinth, where light from distant suns drowns out the faint glimmers of transient visitors. Here, inches the heart of the Milky Way, 3i Atlas lingered undetected for eons, cloaked by the sheer density of its surroundings. The question of why this interstellar comet evaded discovery until 2025 is not merely a story of technological limitations, but a testament to the humility required of astronomers. It underscores a profound truth. The universe is replete with secrets, and our ability to perceive them is constrained by the tools we wield and the biases inherent in our methods. The journey to uncover 3i Atlas reveals not only the ingenuity of modern astronomy, but also the fragility of our cosmic vision. When 3i Atlas first entered the inner solar system, it did so under the shadow of the galactic center, a region so densely packed with stars that even the most advanced telescopes struggle to resolve individual objects. The Milky Way's central bulge, a three-dimensional swarm of ancient stars and interstellar dust, forms a natural barrier to observation. Here, the contrast between the faint glow of a comet and the brilliance of 1,000 stellar neighbors is negligible. For months prior to its official discovery on 1 July 2025, 3i Atlas had passed silently through this stellar gauntlet, its trail obscured by the overwhelming light of the galaxy itself. The comet's hyperbolic trajectory further compounded the challenge. Unlike solar system comets, which follow elliptical paths and often exhibit predictable behavior, 3i Atlas moved at a blistering speed of 61 kilometers per second relative to the sun. Yet, its apparent motion across the sky was deceptively slow, because it approached the solar system from nearly perpendicular to the ecliptic plane, the flat disk where most planetary orbits lie. It did not trace a dramatic arc through familiar constellations. Instead, it drifted subtly against the backdrop of the Milky Way, blending seamlessly into the cosmic noise. This subtlety, combined with the galactic center's glare, rendered 3i Atlas nearly invisible to automated sky surveys designed to detect fast-moving or bright objects. The breakthrough came when the Asteroid Terrestrial Impact Last Alert System, ATLAS, telescope at Rio Hurtado, Chile, flagged an anomaly inches its nightly scans. ATLAS, optimized for detecting Earth-threatening asteroids, relies on algorithms that prioritize rapid changes, inches an object's position. However, 3I Atlas's slow drift and faint magnitude, initially 18, defied conventional detection criteria. It took the collaborative efforts of the Zwicky Transient Facility, ZTF, and amateur astronomer Sam Dean to piece together pre-discovery images from late June 2025. These observations revealed that the comet had been traversing the galactic center's dense star fields since mid-June, a region so crowded that even professional telescopes had overlooked it. The comet's southern origin added another layer of complexity. Most interstellar objects originate from the solar apex, the direction inches which the sun is moving relative to the local standard of rest. Telescopes inches the northern hemisphere, where much of the world's observational infrastructure is concentrated, are naturally biased toward detecting objects inches this region. 3I Atlas, however, hailed from the opposite quadrant of the sky, a direction where fewer telescopes operate. This asymmetry inches coverage meant that its approach went unnoticed for far longer than it might have otherwise. The near miss of 3I Atlas serves as a humbling reminder of the boundaries of our cosmic knowledge. Our current network of telescopes, while impressive, is still a patchwork of capabilities shaped by geography, funding, and historical priorities. The scarcity of large aperture telescopes inches the southern hemisphere has left gaps inches our ability to monitor interstellar visitors approaching from below the galactic plane. Similarly, the reliance on optical surveys, sensitive to reflected sunlight rather than intrinsic emissions, means that darker, slower-moving objects like 3I Atlas can evade detection unless they happen to brighten significantly. This limitation is particularly acute for interstellar objects, which often lack the reflective surfaces or volatile outgassing that makes solar system comets easier to spot. While 3I Atlas eventually displayed a faint coma and potential tail, its initial appearance as a point source mimicked a star or a distant galaxy. The absence of definitive cometary features inches early observations delayed its classification. Only when follow-up spectroscopy confirmed the presence of carbon dioxide, water vapor, and cyanide gas did astronomers conclusively identify it as a comet. This delay highlights the need for multi-wavelength surveys such as those combining infrared, radio, and visible light to disentangle the subtle signatures of interstellar travelers. Moreover, the discovery of 3I Atlas raises questions about how many other interstellar objects have slipped through our net. If a comet of its size and brightness could remain hidden for weeks, what other cosmic wanderers might be lurking inches the shadows of the Milky Way? The answer depends on the sensitivity of our instruments and the adaptability of our search strategies. Future missions like the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, promise to revolutionize this field by scanning the entire sky with unprecedented depth and frequency. Such projects could uncover not just comets like 3I Atlas, but also smaller, darker bodies that have gone undetected until now. The implications extend beyond observational astronomy. The fact that 3I Atlas originated from the galactic thick disk, a reservoir of ancient stars formed inches the Milky Way's turbulent youth, challenges our understanding of interstellar object formation. If the thick disk is indeed a cradle for such comets, it suggests that the conditions for icy body creation were prevalent inches the galaxy's early history. This inches turn could inform models of planetary system evolution and the distribution of volatile materials inches the cosmos. Yet perhaps the most profound lesson from 3I Atlas is the importance of serendipity inches science. Its discovery was not the result of a targeted search, but of a fortuitous alignment of technology, human curiosity, and cosmic timing. The collaboration between professional astronomers and amateur observers, like Sam Dean, exemplifies the power of a distributed network of eyes and minds. As our tools grow more sophisticated, we must also cultivate a culture of openness and cooperation, one that embraces the unexpected and values the contributions of all who look up. The story of 3I Atlas is not merely one of detection and discovery, but of reflection. It compels us to consider our place inches the cosmos, not as passive observers, but as participants inches an ongoing dialogue with the universe. Just as the comet's journey across the solar system offers clues about its origins, so too does its near invisibility challenge us to confront the limits of our own perception. In the grand scale of cosmic time, 3I Atlas is but a fleeting visitor, a messenger from a distant epoch, and yet its arrival stirs a deeper inquiry. What other stories do the stars hold inches their silence, waiting for the right moment and the right eyes to awaken them? As we turn our gaze outward, we are reminded that the universe is both vast and intimate, its mysteries woven into the fabric of every atom and photon that reaches us. 3I Atlas, with its ancient ice and carbon-rich coma, is a relic of a time when the Milky Way was young, a time when the building blocks of life may have been forged inches the crucible of distant stars. Its journey through the solar system is not an end but a beginning, a spark igniting our imagination to explore further, to ask bolder questions, and to embrace the unknown. And so, as 3I Atlas arcs toward its closest approach to the Sun, its fate sealed by the inexorable pull of gravity, we stand at the threshold of a new chapter inches our cosmic saga. What other interstellar wanderers await discovery? What secrets do they carry? And what truths will they reveal about the universe and ourselves? The answers lie not inches the past, but inches the horizon ahead, where the dance of light and shadow continues to unfold. In the vast tapestry of the cosmos, where stars burn like distant embers and galaxies spiral inches silent dance, the discovery of 3I Atlas C/2025 N1 Atlas has illuminated a profound truth. Our solar system is not an isolated island. For millennia, humans have gazed upward, seeking meaning inches the stars. Now, a visitor from the farthest reaches of interstellar space has arrived, bearing secrets etched inches ice and gas, whispering of origins older than our own planetary cradle. 3I Atlas is not merely a wandering comet. It is a cosmic bridge, a vessel of material forged inches the crucible of another star's birthright. As it traces its hyperbolic path through the inner solar system, its fleeting presence stirs a tantalizing question. Could such interstellar wanderers carry the building blocks of life, scattering the seeds of existence across the void? In the shadow of this enigmatic visitor, we stand at a crossroads of science and wonder, where the boundaries of our understanding blur, and the universe reveals itself as both alien and intimately connected. Comets have long been regarded as cosmic snowballs, fragile remnants of the early solar system, composed of ice, dust, and organic molecules. Within our own neighborhood, these icy wanderers have played a pivotal role, inches shaping the conditions necessary for life. Theoretical models suggest that comets delivered water and complex organic compounds to the young Earth, fostering the primordial soup from which life emerged. Now, 3I Atlas complicates this narrative. Unlike the comets of our solar system, which follow elliptical orbits bound to the Sun's gravity, this interstellar interloper follows a hyperbolic trajectory, hurtling through space at a velocity of 58 kilometers per second. Such a speed is far too great to originate from within the solar system. It must have formed inches another stellar system, carried by the gravitational tides of distant stars. The chemical fingerprint of 3I Atlas offers clues to its nature. Observations by the James Webb Space Telescope reveal an abundance of carbon dioxide, alongside traces of water ice, carbon monoxide, and carbonyl sulfide. The Very Large Telescope detected cyanide gas and atomic nickel vapor, elements familiar to solar system comets. These findings suggest that the processes governing the formation of icy bodies are not unique to our corner of the galaxy. If 3I Atlas shares similarities with comets born inches our own system, it implies that the mechanisms responsible for assembling volatile rich materials are universal. Such universality raises a compelling hypothesis. If comets can carry the ingredients for life inches our solar system, might they do the same elsewhere? Could interstellar comets serve as cosmic carriers, ferrying the raw materials for biology across the galaxy, seeding nascent planets with the precursors of life? The comet's origin story deepens this mystery. Tracing its trajectory backward through time, astronomers have determined that 3I Atlas hailed from the Milky Way's thick disk, a region populated by ancient stars, some of which are billions of years older than our Sun. The thick disk is a relic of the galaxy's formative years, a place where stars and their attendant comets have wandered for eons. If 3I Atlas is indeed 7 to 14 billion years old, as recent studies suggest, it predates the solar system by over 3 billion years. In that span, it may have traversed countless star systems, its icy nucleus preserving molecular echoes from epochs when the galaxy was young. Such an object is not merely a transient visitor, it is a living archive, a time capsule from the dawn of the cosmos. Yet the comet's journey is not purely one of preservation. As 3I Atlas approaches the Sun, its icy heart warms, and the delicate balance of its chemistry begins to shift. Sublimation of frozen gases creates a glowing coma, a tenuous veil of vaporized material that may contain complex organic molecules. These molecules, forged inches the cold depths of space, could include amino acids or other biologically significant compounds. While direct evidence of such molecules inches 3I Atlas remains elusive, their presence inches solar system comets provides a tantalizing precedent. If interstellar comets share this chemistry, they might act as natural laboratories for prebiotic reactions, synthesizing the molecular scaffolding of life inches the vacuum between stars. The hyperbolic excess velocity of 3I Atlas, its speed relative to the solar system, further underscores its interstellar heritage. Unlike 1I Oumuamua and 2I Borisov, which arrived from directions aligned with the Sun's motion through the galaxy, 3I Atlas hails from the southern celestial hemisphere, a region where astronomers anticipated fewer interstellar visitors. This anomaly challenges assumptions about the distribution of interstellar objects, hinting that such wanderers may originate from diverse galactic environments. If true, it suggests that the Milky Way's thick disk with its ancient stellar population is a prolific source of comets. These comets, ejected from their home systems by gravitational interactions, drift through the interstellar medium for eons, occasionally crossing paths with other stars. In doing so, they become agents of exchange, carrying material between stellar nurseries and planetary systems. The implications of 3I Atlas's existence ripple outward, touching upon fundamental questions about life's origins and the universe's interconnectedness. If interstellar comets routinely traverse the galactic expanse, they may act as cosmic messengers, transporting the molecular blueprints of life from one planetary system to another. This idea, once the realm of speculation, now gains traction through the lens of astrophysics. Consider the scenario: a star system birthing a new planet, its volatile rich comets ejected into the void. Eons later, one such comet collides with a fledgling world elsewhere, delivering water, organics, and perhaps even microbial spores. Could life arise independently on multiple worlds? Or might it hitch a ride on these interstellar travelers, spreading like wildfire through the cosmos? 3I Atlas, with its ancient lineage and chemically rich composition, becomes a Rosetta Stone for decoding this cosmic dialogue. Its nucleus, shielded by layers of ice and dust, may harbor molecules unaltered since the galaxy's youth. Studying these materials could provide insights into the primordial conditions that preceded life, revealing whether the building blocks of biology are common or rare inches the universe. For instance, the detection of cyanide gas inches 3I Atlas mirrors findings inches solar system comets, where such compounds play a role inches forming amino acids. If similar processes occur inches interstellar comets, they might serve as crucibles for prebiotic chemistry, generating the molecular diversity needed for life to emerge. However, the potential for life aboard 3I Atlas remains speculative. While the comet's chemistry aligns with the requirements for biology, the absence of liquid water and energy sources makes it an unlikely habitat. Still, the mere possibility that such objects could transport life's precursor underscores their significance. Imagine a future where spacecraft intercept interstellar comets, sampling their contents for signs of extraterrestrial biochemistry. Such missions could revolutionize our understanding of life's ubiquity or rarity inches the cosmos. Until then, 3I Atlas serves as a reminder that the universe is not a silent void, but a dynamic web of exchange, where the fates of stars, planets, and perhaps even life itself are intertwined. The comet's age further amplifies its role as a cosmic relic. At 7 to 14 billion years old, it predates the solar system by billions of years, surviving epochs when the galaxy was turbulent and chaotic. During this time, it may have passed through regions of intense star formation or drifted through the galactic halo, encountering supernovae and black holes. These experiences could have altered its composition, embedding it with isotopes or compounds forged in stellar furnaces. By studying 3I Atlas, scientists hope to reconstruct the history of the Milky Way's thick disk, unraveling the evolutionary pathways of ancient stars and their attendant comets. Yet, the study of interstellar comets is fraught with challenges. Their fleeting visits make detailed observation difficult, and their faintness limits the data we can extract. 3I Atlas, for instance, will not come closer than 1.8 AU to Earth, rendering it invisible to the naked eye. Only advanced telescopes, such as Hubble and James Webb, can pierce its coma to glimpse its nucleus. Future technologies, such as space-based interferometers or dedicated interstellar probes, may offer deeper insights, but for now, we rely on snapshots of these visitors, piecing together their stories from fragments of light. As 3I Atlas continues its brief sojourn through the solar system, its legacy endures the questions it inspires. What other interstellar wanderers lie hidden the dark, waiting to be discovered? How many have already slipped past unnoticed, their trajectories etched the faintest glimmers of starlight? The comet's passage is a reminder that we are not alone the cosmos, not the sense of sentient beings perhaps, but the shared heritage of matter, energy, and the relentless drive toward complexity. In the next segment, we turn our gaze inward, reflecting on the lessons 3I Atlas imparts about our place in the universe. How does the existence of interstellar comets reshape our understanding of life's origins? What responsibilities arise as we recognize the interconnectedness of all things? As the comet fades from view, its message lingers. The universe is a vast, intricate web, and every star, every planet, every comet is a thread its grand design. Let us follow this thread, step by step, into the unknown. On a clear night, July 2025, the Atlas telescope at Rio Hurtado, Chile, captured a faint smudge against the backdrop of the Milky Way. At first glance, it seemed no different from countless other transient objects flitting through the heavens. Yet, within days, this speck revealed itself to be something extraordinary, a visitor from beyond the solar system, designated 3I Atlas, or C2025N1. Atlas, the comet's discovery, marked a pivotal moment in astronomy, a third interstellar wanderer to cross our cosmic neighborhood. While the first, 1I Oumuamua, had appeared as a mysterious cigar-shaped asteroid in 2017, and the second, 2I Borisov, had glided through the inner solar system in 2019 as a textbook comet, 3I Atlas carried its own unique story. Its arrival was not a fleeting curiosity, but a profound reminder of the universe's boundless scale and the interconnectedness of its far-flung realms. The comet's trajectory told a tale of cosmic adventure, moving at a blistering 58 kilometers per second relative to the Sun. 3I Atlas followed a hyperbolic path, an open curve that would carry it back into the interstellar void after a brief encounter with the solar system. Unlike the elliptical orbits of native comets, which loop back to their points of origin, this object's path was unbound, a testament to its extraterrestrial provenance. Its closest approach to the Sun would occur on October 29, 2025, at a distance of 1.36 astronomical units, AU, between Earth and Mars. Though it would never come closer than 1.8 AU to Earth, its presence stirred a quiet sense of wonder among scientists and stargazers alike. After all, here was a fragment of another star's history, a relic of stellar nurseries long vanished, now traversing a realm it had never called home. Yet 3I Atlas was more than a mere interstellar nomad. It was a messenger, a vessel of ancient secrets waiting to be deciphered. Its composition, revealed through the lenses of the Hubble and James Webb space telescopes, hinted at a chemistry unlike anything in our solar system, rich in carbon dioxide, with traces of water ice and cyanide gas. It bore the fingerprints of a different cosmic recipe, and its age, estimated to be billions of years, placed it inches an era when the Milky Way itself was still young. As astronomers turned their eyes skyward, they were not merely observing a comet, they were peering into the distant past of a galaxy teeming with mysteries. The journey of 3I Atlas began long before it entered our solar system, tracing a path through the Milky Way's thick disk, a sprawling ancient layer of the galaxy, where stars older than the Sun drift inches slow, tilted orbits. Unlike the thin disk, where younger stars like our own orbit inches tight, flat spirals, the thick disk is a chaotic tapestry of stellar motion. Stars born here have traveled vast distances over eons, their trajectories shaped by gravitational tides and collisions. It is here, amidst this stellar debris, that 3I Atlas likely formed. The comet's origin was deduced through careful analysis of its velocity, by breaking down its hyperbolic excess speed into galactic coordinates. Astronomers determined that 3I Atlas approached the solar system from a direction near the galactic center. Its radial velocity component, U, indicated it was moving away from the Milky Way's core, while its vertical velocity, Watts, suggested it was ascending above the galactic plane. This combination placed it firmly within the thick disk population, a group of stars and objects characterized by their high metallicity and ancient origins. Studies led by Matthew Hopkins and Asta Taylor, Inches 2025 estimated 3I Atlas's age between 3 and 14 billion years, making it potentially older than the solar system itself. Such an age implies the comet predates the formation of our planetary family, surviving the violent births and deaths of countless stars. But how did this ancient fragment escape its stellar cradle? The answer lies in the dynamic forces of the galaxy. Gravitational interactions with massive stars or passing molecular clouds could have dislodged 3I Atlas from its home system, sending it hurtling into interstellar space. Over billions of years, it drifted through the galactic expanse, its icy nucleus preserved the cold vacuum of deep space. Only when it neared the solar system did the sun's gravity awaken it, triggering the sublimation of its frozen layers and igniting the coma that now surrounds its nucleus. The comet's activation was a spectacle of transformation. As sunlight struck its surface, volatile ices, primarily carbon dioxide, but also water and carbon monoxide, turned directly into gas, releasing fine dust particles inches the process. This material formed a glowing envelope, or coma, around the nucleus, and inches some cases, a tail stretching millions of kilometers. Observations by the Very Large Telescope revealed the presence of cyanide gas and atomic nickel vapor, elements commonly associated with solar system comets, but whose abundance 3I Atlas hinted at a distinct evolutionary history. The James Webb Space Telescope's infrared sensors further unveiled the comet's chemical complexity, detecting signatures of carbonyl sulfide, a molecule rarely observed in native comets. Together, these findings painted a picture of a body shaped by conditions alien to our own corner of the galaxy. Despite its scientific richness, 3I Atlas posed a challenge for observers. Its faintness peaking at magnitude 11.5 meant it required large telescopes to glimpse its details. From Earth, it remained elusive, hidden inches the glare of the sun during its closest approach and visible only briefly before and after perihelion. Yet for those with access to advanced instrumentation, the comet offered a rare opportunity to study an interstellar emissary inches real time as it traced its hyperbolic arc. It became a focal point for global collaborations, uniting amateur and professional astronomers inches a shared pursuit of knowledge. To stand beneath the night sky and witness 3I Atlas is to confront the vastness of time itself. This comet, born inches an epoch when the Milky Way was still assembling its spiral arms, has outlived civilizations, species, and even entire planetary systems. Its journey through the galaxy is a silent testament to the resilience of matter and the enduring power of gravity to shape destinies across eons. For humans, who measure time inches generations and lifetimes, the comet's age is almost incomprehensible. 7 billion years, a span that dwarfs the 4.6 billion year history of the solar system, places 3I Atlas inches a category of cosmic longevity reserved for the oldest stars inches the galaxy. To hold a sliver of such antiquity inches our gaze is to touch the edge of eternity. Yet 3i Atlas is not merely a relic of the past. It is a bridge, a physical link between distant stellar systems and our own. Every atom inches its nucleus, every molecule inches its coma, carries the chemical signature of its birthplace. By studying these signatures, scientists hope to unravel the processes that govern the formation of comets, and by extension, the building blocks of life inches other parts of the galaxy. The presence of carbon dioxide and cyanide gas suggests that 3i Atlas's parent star system may have hosted conditions favorable to organic chemistry, a clue that could reshape our understanding of the prevalence of life-supporting materials inches the cosmos. If such compounds are common inches interstellar comets, it raises profound questions about the universality of the ingredients necessary for life. Moreover, 3i Atlas's trajectory offers a window into the dynamics of the Milky Way. The fact that it originated from the thick disk rather than the thin disk challenges assumptions about the distribution of interstellar objects. Previous discoveries of Oumuamua and Borisov had pointed toward the solar apex, the direction of the sun's motion, as a likely source for interstellar visitors. Yet 3i Atlas's southern origin defies this pattern, suggesting that the galaxy's gravitational architecture may be more complex than previously thought. Its high vertical velocity component indicates it has traveled far above and below the galactic plane, a path that could intersect with diverse stellar environments. By mapping the paths of future interstellar objects, astronomers may uncover hidden structures within the Milky Way, revealing how its gravitational tides sculpt the motion of rogue bodies. For those who ponder the meaning of such discoveries, 3i Atlas serves as a humbling reminder of our cosmic insignificance. In the grand tapestry of the universe, our planet is but a single thread, woven into a fabric that stretches billions of years inches all directions. The comet's passage through the solar system is a fleeting event inches the context of cosmic time, yet it carries the weight of epochs. It is a reminder that we are not isolated inches the cosmos, but part of a vast, interconnected web of matter and energy. Every star we see, every nebula we admire, and every interstellar traveler, like 3i Atlas, is a piece of a larger story, one that transcends the boundaries of time and space. As 3i Atlas arcs away from the sun and into the abyss of interstellar space, its departure leaves a lingering question, inches the minds of those who observed it. What other secrets lie hidden inches the darkness? The universe is a vast repository of mysteries, and this comet is but one of countless envoys waiting to be discovered. Will future interstellar visitors bring new insights into the origins of the galaxy, or will they challenge our most cherished theories? Perhaps one day, we will intercept a body carrying evidence of alien worlds, or a signal encoded inches its chemical composition. For now, 3i Atlas remains a beacon of possibility, a whisper from the depths of the cosmos urging us to look farther, to ask bolder questions, and to embrace the infinite unknown. This script expands the original segment into a contemplative narrative, weaving scientific detail with cosmic wonder. Each section delves into the comet's discovery, origin, and implications, while maintaining a lyrical tone that reflects the awe of the universe. The structure adheres to the specified framework, ensuring a smooth transition between themes while emphasizing humanity's place inches the grand cosmic timeline.